We are currently living through an explosion in artificial intelligence, but that excitement is masking a massive hidden cost. This chart models a deeply unsustainable trajectory. By the year 2030, global data center power consumption is expected to multiply 13 times over. The root cause of this energy crisis comes down to basic physics. For decades, we have relied on pushing electrons through copper wiring to process data. But as the sheer volume of data scales up, electrical resistance generates tremendous heat, requiring even more power to cool down. You can see this technological ceiling in this chart, tracking the memory gap. The top line shows hardware processing power scaling up rapidly, but the lower lines, the bandwidth of electrical connections, are flatlining. We can process data quickly, but can't move it fast enough. To hit international carbon-neutral targets while continuing to advance AI, we must move past electricity as our primary data carrier. That is the objective of a massive infrastructure project spearheaded by NTT called IOW. IOW stands for Innovative Optical and Wireless Network. Its core technical principle is a shift from the electron to the photon. Traditionally, we have only used light for long-distance internet transmission, wrapping colorful optical strands in thick protective casing to drag data across ocean floors. But once that optical data reaches a server, it still gets translated back into electricity. NTT's breakthrough was engineering optoelectronic fusion devices, hardware that brings light directly inside the computer itself. This roadmap shows the progression. They replace electrical wiring between circuit boards with optical connections, eventually weaving light pathways directly into the chips. By substituting wiring with optical waveguides, marked in red, data moves without electrical resistance. No friction means no heat. This microscopic shift breaks the thermal and energy barrier that currently restricts modern computing. When you take that principle and apply it to a global network, the efficiency gains multiply. Right now, the internet sends data by chopping it up into little pieces called packets. When a packet reaches a router, the system momentarily converts the optical signal back into electricity just to read the destination. This causes a microscopic delay. Iown's all-photonics network eliminates this step, allowing data to travel end-to-end as a single, unbroken beam of light. Combining these microscopic chip designs with a macroscopic optical network results in 3 specific, measurable benchmarks. Power consumption drops to 1/100th. Transmission capacity increases 125 times over, and latency is cut to 1/200th. That specific drop in latency, reducing communication delays by a factor of 200, effectively removes the physical distance between digital tools. In early tests, the all-photonics network achieved a transmission delay of just 20 milliseconds across the massive 700-kilometer gap separating Tokyo and Osaka. That means a conductor in one city can direct an orchestra spread across the country, playing perfectly in sync. It means a patient with ALS can use real-time neural signals to control a digital avatar without a perceptible lag between thought and action. For mobility, it allows an autonomous car speeding down a highway to instantly download safety and traffic data from a remote grid, reacting to hazards faster than humanly possible to achieve a zero-traffic accident society. By erasing network delay, fragmented machines and distant users can finally operate together as a single instantaneous nervous system. Then there is the 125-fold increase in data capacity. This sheer volume of bandwidth is a requirement for the next evolution of artificial intelligence. Instead of relying on single, massive AI models, we can build AI constellations. Multiple, specialized AIs can connect and collaborate in real time to solve complex logic problems that would immediately crash a standard electrical network. And this capacity extends beyond the atmosphere. Right now, observation satellites are bottlenecked, forced to send data back to Earth using slow radio waves. The IOWN roadmap builds a space-integrated critical network. By using optical lasers, satellites will instantly share and process massive amounts of high-resolution data directly in orbit, beaming down only the essential insights. Massive optical capacity allows our most advanced computing projects to scale beyond the limits of earthly infrastructure. Which brings us back to the energy crisis we started with. We have strict international goals to reach carbon neutrality, but our data demands show no signs of slowing down. Because of optoelectronic principles, these massive computations, from orbital satellite networks to collaborative AI constellations, can operate on a fraction of the power required by copper wiring. It gives us the energy budget to run digital twin computing, vast, sustainable simulations of real-world environments that help us predict and solve complex human problems without draining the electrical grid. This technology has already left the lab. Commercial APN services are actively rolling out, and this optical infrastructure will be a focal point of the 2025 Osaka Kansai Expo. Iown is more than a faster network. By moving from electricity to light, it provides the physical, sustainable architecture that makes our most data-heavy ambitions possible.